Hi. Yes! 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 Note to self, don't behave like an idiot in a lab. Today, in this video, I'm going to talk about DC motors. First of all, what on earth is an electric motor? In my previous videos, i.e. the ones electricity basics and series 1 and shunt motors, I have explained what they are. Please refer to them before you watch this video. An electric motor is a device which converts electrical energy into mechanical energy. There are motors which can run on AC only. These are known as AC motors. This is a practical example of an AC motor. It is an induction motor. There are motors which can run on both AC and DC. These are known as universal motors. Here is a practical example of a universal motor. This was the washing machine motor I've showed you in my previous videos. It is a series wound universal motor. And there's the motor which only runs on DC, which is known as a DC motor, like this. This is a 12 volts DC motor. There are many types of DC motor, some of which include the permanent magnet DC motor, the series wound motor, the shunt motor, the compound motor, and the brushless DC motor. In this video, we will be focusing on the brushed DC motors. Those are the permanent magnet DC motors, the series 1 DC motors, the shunt DC motors, and the compound DC motors. I will talk about brushless DC motors in another video. In brushed DC motors, you have the field winding, or permanent magnets, to induce a magnetic field in the motor, an armature winding, which is in the motor. You see that's brown, that is the armature winding. The commutator, which is this. The brushes, which are these, hence the name, brushed DC motor. And the body of the motor. In this motor's case, instead of permanent magnets, we have field windings. This small DC motor, however, has permanent magnets, as you can see here. This motor is a series wound motor, as I've previously said. Series wound, shunt, and compound motors have a field winding. This can be connected either in series with the armature, in parallel with the armature, or in both series and in parallel. An electric current is taken to the armature by the brush and commutator. Electricity flows through the brushes. These are normally made of graphite, but they can also be made out of metal, but they are normally made out of graphite. These brushes are attached to commutators. In DC motors, we use commutators, not slip rings. Commutators. This commutator has many segments, as you can see. And these segments touch to the brush and make a contact with a winding of the armature. And the current flows through a winding and induces a magnetic field. The motor turns a bit. This changes the contact of the commutator onto another winding, and it turns again, and this process repeats and repeats, thus making the DC motor spin. If the field winding or permanent magnet is giving us a magnetic field, that is, and add not a changing one, a constant one. For this means that in the armature we have a changing magnetic field. The commutator gives a changing magnetic field in the armature as for this to turn. I'm going to show you a practical example of what I just said. This is a permanent magnet DC motor. Okay, the only difference between those two is that here we have permanent magnets instead of field winding. And this is my power supply, i.e. a 9-volt battery. And I'm going to show you in practical what just happened. Okay, so this motor has bad contacts, so I'm going to use this one. Same thing, they're both PMDC motors, permanent magnet DC motors. As you can see, it is spinning. What you just saw there was what I said happening many times per second. The entire process, the commutator changing connection, the brushes sparking, and etc. That is happening many times per second. Unfortunately, there are some disadvantages to brushed DC motors. One of which is that on the contacts of the brushes and commutator there are sparks. It can be the case that when the commutator switches connection, there is a spark, and that may not be very good especially in situations where you have explosive gases like hydrogen. How on earth are these generators if they have no permanent magnets? Well, there is something called self-excitation, when the generator excites itself and gives out electricity. This is when there's residual magnetism in the generator, and a bit of electricity is generated in the armature. This little bit of electricity is transmitted to the field winding, which gives an even stronger magnetic field, which generates electricity from the armature winding, and it excites that way. Motors are used. DC motors are used in many applications. Some examples would be forklifts, baby toys, and many other examples. In forklifts, you will normally find a shunt motor, because a shunt motor's speed is independent of load. In a baby toy, however, you will normally find a small permanent magnet DC motor. Series motors can be found in washing machines, but they're not always series motors. Some are induction motors. This is a washing machine series wound motor. I've showed you this in my previous videos. Because most appliances include universal motors, you find series wound motors in most domestic appliances. Not in most appliances, in most domestic appliances. For the sake of the viewers, I'm going to open up this puny, small, tiny, broken DC motor for you to see the insides. It was broken anyway, so why not? Okay, so I apparently can't take the armature out because here is rusted. So let's start with the obvious parts. These are the makeshift brushes. In this case, they are metal. This is the commutator. What you're seeing here is the commutator, this brownish part. This big brown part here, this is the armature winding. You normally find armatures like these in small DC motors. In larger DC motors, you will have more than just 3 poles. And these two are the permanent magnets on the side. They're the permanent magnets. Okay, so after some hard work, I managed to take apart the motor. As you can see, these are the brushes, the makeshift brushes, which lead to the contacts of the motor. The armature fits here. The commutator goes here. The commutator, and it gives a changing current into the windings, which in this case are these. This is the armature winding. This is the body of the motor, and where the permanent magnets are. Here are the permanent magnets, 1 and 2, with a screwdriver. As you can see, there's a magnetic field and they get attracted, so these are permanent magnets. When I put this setup together and apply power to it, the brushes supply power to the armature, and because the armature has a changing magnetic field, this makes the field winding magnetic flux turn the armature winding. Thus, the motor will operate. I'll just have to try to be careful not to give too much voltage, or things won't end well. I'm turning the shaft by hand. This in itself, like this, is a generator, because there's a moving conductor in a magnetic field. The moving conductor is the armature winding. I am turning the conductor, which in this case is the wire, around the permanent magnets, which give out the magnetic field. Hence, I'm generating electricity this way. Note that I'm not generating a lot of electricity, because this is only a 3-volt motor. And this spins at a very high RPM when 3 volts of potential difference are applied to the terminals at high enough current. Okay, it should see a bulb light when I turn the generator. I'm turning the small DC generator in my hand, As you see, the multicolored sub-circuit's bulb is lighting up. For some reason, when I turn it in the other direction, it lights up. Note that if I turn a DC generator in one direction, it gives electricity. It gives a current in one direction. If it is a DC generator, that is. And now we have learned the basic construction of small DC motors. Note that in larger DC motors, not only do they have more poles, they have more segments on the commutator. Congratulations! You have now learned the basic construction of DC motors. Thank you for watching, hope you enjoyed.